Hello, class. We're about to start section 5.1 through 5.3 for tonight's class. Okay, starting with section 5.1, we're on pages 496 to 498, and we're supposed to do problems 1 through 4 all. Okay, so what I'm going to do, like I traditionally have done, I'm going to only do a few select problems, and those two problems will be problems 2 and 4. So starting with problem number 2, problem number 2 is on page 497. So we look here at A. It says sketch the graphs of the following pair of functions on separate coordinate systems. Use labels or colors to differentiate the graphs. Verify your sketches using your graphing calculator. Okay, so basically they want us to graph here, and you can see this in your textbook. They have f of x, but we're going to use y. Y is equal to 5 divided by x. That's one graph. Now we see that that is in red. And then we would do another graph. And we would do y is equal to negative 5 divided by x. And as you see, this is in blue. So what we could do here, just for the sake of this here so you can see the difference, let's turn this off. So this would be y is equal to 5 over x. And you could pause it and copy this. Or you could go here and you have y is equal to negative 5 over x. Or if you want to, you can take a look at both. Okay, so that basically takes care of A. Now we go here to B. Okay, for some reason it's not allowing me. Okay, let me do this. I have to shrink this up here. Okay, so now we're going to go to B. So with 2B, it says describe how the graph of G can be obtained from the graph of function f. Okay, so basically the change in sign results in opposite output values. And we know opposite output values are basically our y values. The graph G is the reflection of f about the x-axis or the y-axis. And that is basically it for problem number 2. Now we move on to problem number 4. Okay, problem number 4 starts on page 498 and is broken up into parts A through H. It says the speed limit on Route 66 in parts of Arizona is 75 miles per hour. So we go here to 4A. It says if you maintain an average speed of 75 miles per hour, how long would it take to make a 350-mile trip on Route 66? Okay, so the first thing we need to do is write down the distance formula. The distance is equal to rate times time, or it could be written as t is equal to distance over rate. So it'd be time is equal to distance over rate. And then of course, we could say where t is the time, so we can designate the values. And we know d is the distance, and r is the average rate. So in this case, t is equal to 350 over 75, which would give us 4 2/3 hours. Okay, so, or this could be broken down to 4 hours and 40 minutes. Now let me show you what exactly went on here. Okay, so according to the problem, we did a 350-mile trip, which was our distance. That's where we get the 350 from. And then it said that we did it at 75 miles per hour, which is our rate. So that's where we get the 350 divided by 75. And then you can put that in your calculator. So you add 350 divided by 75. And it gives you 4.666. And then we know that when you have a decimal with repeating sixes that never end, and we know that this last one was rounded, that's really 2/3. So this is where we get the 4 2/3 hours from. Because when we click here, it's just going to give us this fraction here. 3 goes into 14 4 times with 2 left over. So this is how we get the 4 2/3 hours. But then you may be asking how we get the 4 hours and 40 minutes. So basically we could do this. We see how we get the 4 hours by the whole number. But to get the 40 minutes, we know that in 1 hour there are 60 minutes. So if we went off to the side and took 2/3 times 60, 3 goes into 3 ones, 3 goes into 60 20 times. 2 times 20 is 40, and that'll be 40 over 1. So that's how we get our 40 minutes. Okay, so now that took care of A. Now we move on to B. It says write an equation that defines t as a function of r, in which r represents the average speed in miles per hour and t represents the time in hours to complete the 350-mile trip. Okay, so now remember, we wrote this other formula here. T is equal to distance over rate. Now they want us to write the formula in terms of t, which we already have here, but they want us to use the 350 miles for the trip. So it just be t is equal to 350 over r. Now that would be B. Now we go here to C. Now C, we have a table. I'm going to abbreviate the table and put R and T here. So we had 25, 35, 45, 55, 65, 75, and then finally 85. Okay, so now it says complete the following table for the equation you determined in part B. So what we need to do is substitute these values in for R, and then that will give us our T. So what I could do is this here. Our equation make T y is equal to 350 and divide that by X. Matter of fact, let me turn off these graphs here. Okay, so we have this here. So what we could do is we could hit this wheel and hit the table. And all we have to do is type in the values. So we type in 25. It gives us 14. Then we type in 35. It gives us 10. 45. It gives us 7 points. So we around the 1 decimal place. So it'd be 7.8. 55. It'll give us 6.4. 65. It'll give us 5.4. 75. It will give us 4.7. And then finally 85. It'll give us 4.1. Okay, so now We have our values here for C. And so we're done with C. Now we're going to move on to D. Now D, it says, as your average speed increases, what happens to the time it takes to complete the trip? Well, if your speed increased, then the time it takes will decrease. So it decreases, but it decreases more slowly as the rate as R increases. Yeah, instead of just putting a rate. So it decreases, but it decreases more slowly as R increases. Okay, now we come to E. It says, as your average speed for the trip get closer to zero, what happens to the time it takes to complete the 350-mile trip? The time increases very rapidly as the rate approaches zero. So basically, as your rate of speed approaches zero, that means that it takes more time to get to your destination. So we go here to F. It says, what is the practical domain? Now, of course, when you're talking about a practical domain, you're basically looking here in quadrant 1 when you're talking about a practical domain, because one thing we know that our rate of speed cannot be negative. And then we also know that according to our table, we only went to 85. So basically, the practical domain is the rate will be greater than 0, but less than or equal to 85, according to our table and according to what we have here. Now, they ask us here to sketch a graph. So since we know that this is the practical domain, this is where we would actually have our graph. And if you click on a few points here, it gives you a few points that you could use. And of course, you could look here at this table as well. And you notice here when it gets to 2, it goes up to 175, but it never quite hits 0. All right. So, and they just want us to sketch the graph of the practical domain. Okay, H. What are the vertical and horizontal asymptotes of the graph of the function? All right. So we go here to H. So we'll say the horizontal asymptote is t is equal to 0. The vertical asymptote is r equals 0. If you notice, this graph here does not hit the x or y axis at 0. It gets very, very close, but it does not hit at 0. So it never gets 0. It approaches 0, but never hits 0. Okay, so that is our vertical and horizontal asymptote. And so now we are done with section 5.1. Okay, class, so now we're going to go over to 5.2, which basically starts on page 505 to 510, and it's 1 through 11 odd. So I am going to pick out a few problems for us to do. And one of the problems is going to be problem number 3 and problem number 7, problem number 9, and problem number 11. So we would do problems 3, 7, 9, and 11. So we'll practically do, just about all of the problems. So starting with number 3 on page 507, It says match the following functions with the accompanying graphs. Okay. So the first thing that I would want to do, in fact, let me get rid of all of this and let me expand this here. Okay, first of all of these we're going to have y is equal to 10 divided by, we will have x, and I have to take that to the fourth power, x to the fourth power. Okay, so we have y is equal to 10 over x to the fourth power. And as you all can see, this graph here actually goes with b. So for 3, that, well, okay, so I guess it's listed as 3i, then we would have that as b. And then I guess we would have to do 3i2. And I know these are Roman numerals, but I don't want to say 3, 2, 3, 3, and all of that. So just bear with me with saying the I portion. Okay, so I listed them here, but 3i was B. So now I could turn that off. And then we can go to the next, which is I2. So we have y is equal to 100 divided by, and then we would do x to the fifth power. All right, let me expand this out. Now, if we look here, the only one that fits that bill is actually C. All right, now we go to the next. We will have y is equal to negative 10 divided by x to the third power. And as you can see here, the only one that fits that bill is actually A. And then last but not least, we still should check it. It'll be y is equal to negative 1 divided by x squared. And I will turn this off. And as you all can see here, oh, wait a minute, this one is on. As you all can see here, that would be D. So those are our solutions for problem number 3. Okay, problem number 7. Problem number 7 is on page 508. It says complete the following tables of ordered pairs for the given inverse variation. Determine the constant of variation and write the equation that is represented by the table. Now it says y varies inversely as x. Okay, so this is 7a. So let me do this table. So we have x is 1/2. We have 1, 2. Then we have 2, and we have 6. Okay. Now, when they say y varies inversely, that's y equals k over x. Now, what we must do first, we need to find out what k is equal to. Now, the only one of these that we have where we have an x and y is this 1 and 2. So we will substitute those values in for x and y and solve for k. So 2 is y and x is 1. So we know k over 1 is just k. So now our new formula would be y is equal to 2 over x. So that will be your final answer for A. Now we go here to B. Have another table. So we have x and y. So we have 1/2. We have 1. We have 2. And we have 6. And this 2 has 1 with it. So let's say y varies inversely as x cubed. So the inverse formula here would be y is equal to k over x cubed. Now the only values that we have both of them for is the 2 and the 1. So we'll substitute in 1 for y, and we'll substitute in 2 for x. So this would be 1 is equal to k over 8. Now we need to get rid of this 8 from our denominator by multiplying each side by 8. So 8 is equal to k. So now our new formula, or our inverse formula, would be y is equal to 8 over x cubed. And that is the final answer for B, for problem number 7. All right, our next problem is problem number 9. Now with problem number 9, it says the amount of current I in amps in the circuit varies inversely as the resistance R in ohms. A circuit containing a resistance of 10 ohms has a current of 12 amperes. Determine the current in a circuit containing a resistance of 15 ohms. So the first thing is our inverse formula is I is equal to K over R. Now, we're given that a current containing a resistance of 10 ohms. So we're given R is 10. And then it says we also are given, it says it has a current of 12 amperes. So we have the I as well. So then that would be 12. So now we would substitute and then solve for K. So we have I is 12 is equal to K over R is 10. Now we have to get K by itself, so we'll multiply each side by 10, and that'll be 120 is equal to K. So now our formula would be I is equal to 120 over R. Now they say determine, now this is one part of our answer. Now it says determine the current in a circuit containing a resistance of 15 ohms. So what we would do is substitute in 15 for R. So we have 120 divided by 15, which will give us 8 amps. So I is equal to 8 amps. So both of these, the formula and also the final answer. Okay, so now we go to our final problem, which would be problem 11. And it's on the same page as problem 9, page 509. So with problem 11, we have a table here. Let me draw the table first. So we have P and we have V. So it'll be 20, 82, 30, 54, 40, 41, 50, 32, 60, 27, 70, 23, and then 80, 20. Okay, so now it says sketch a graph of the data. Okay, so what I want to do, I want to first get rid of all of this, and then I can do a quick table, and I could put in the values. Okay, so we will have 20, 30, 40, 50, 60, 70, and 80. And you have 20, 82, 30, 54, 40, 41, 50, 32, 60, 27, 70, 23, then 80, 20. Okay. Now we can click this zoom fit so we can see those points. So that would take care of 11A as far as drawing a sketch. Now, one thing that we need to talk about is your P and V values. Now, your P represents the x-axis. So this right here would be the p-axis, and this here would be the v-axis. Then you would just have to determine the values that you will have on the axis, and it just depends on how big your graph is. But looking at the graph in the book, it looks as though the p-axis should go by 5s, and then the v-axis should also go by 5s, because you would end up getting to 95 with both of them. So that would cover everything. Okay, so now we're done with 11a. Now we're going to go to 11b. Now 11b, it says one possible model for the data is that v varies inversely as the square of p. Does the data fit the model v equals k over p squared? Explain. Okay, so b, they give us the model v is equal to k over p squared. Now, we can do this. We can say no, and the reason being is if we use p equals 20, v would equal 82. So we would have k is equal to 20 squared times 82, which is 32,800. Now, just to go back over this, just to make this a little bit more cleaner. Since we have P is 20, V is 82, this is our formula. We're basically substituting in the values here. V would be 82, P would be 20. And we know, well, let me write it out. So we have V is equal to K over P squared. So V would be 82, K we don't know, and then P is 20. So we will have to multiply each side by 20 squared, which we know 20 squared is 400. So we have 20 squared times 82 is equal to K. So we already figured out that that's 32,800 is equal to K. So now we have V is equal to 32,800 for K all over P squared. Now, if we put in 30 for P, because we have to test this, 32,800 divided by 30 squared. Now, this will give us V is equal to 32,800 divided by 900. And when we divide this out, it will give us an approximate value of 36.44. Now, if you look at this 36.44, if you look at this, 30 is at 54. This is not even close. That's why it's no. Okay, now we move on to C. Okay, C, it says another possible model for the data is that V varies inversely as P. Does V equals K over P model the data? Okay, let's take a look at that. So we have V is equal to K over P. So we could pick those same values where P is 20 and V is 82. So we would have 82 is equal to K over 20. Oh, for some reason, the camera went kind of light on me. All right, so we'll multiply each side by 20. So if we multiply 20 times 82, that'll give us 1,640 is equal to K. All right, so our new formula would be V is equal to 1,640 all over P. All right, so now we're going to try another value. Let's try it with 30 this time. So P would be 30. So we have V is equal to 1640 divided by 30. And then that'll be approximately 54.67. Very, very close to what we have here. It's not exact, but it's close. All right. So we have 54.67, which is very, very close. And I don't know what has happened to the light here, but it seems very, very light now. So let me try a different writing utensil. Okay, so now we're going to try a different value. Oh, that didn't help much. Well, let me try this with 40. So we have 1640 divided by 40. So 1640 divided by 40, if we put it into our Desmos calculator, that would give us, actually, it would give us exactly, not approximately, 41. So if you look back up here at 40, it does give us 41. So this would be a yes. And we could say it is very close. All right. So now we go here to D. It says predict the volume of the gas if the pressure is 65 pounds per square inch using a graph in part A. Okay, so they want us to use the graph, and they tell us that the pressure is 65 pounds. So what we could do, we could take 1640. Now they told us to use the graph. So, okay, so what we would do the graph. Remember our formula is y is equal to 1640 divided by, and we would just say x, we'll make px, and you see that it's hitting all of these points, even though it's not exact. And then what we would do here, we would substitute in, well, we actually can drag this here. And we need to go to 65. Yeah. So it says here 65 is about 25.23. So we could just say, about 25.2, something about there. So we could say this approximately 25.2. So for D, we could say V is approximately 25.2 cubic feet. And then finally E, it says verify your answer in part D using a model from part C. So basically what we could do, we could just substitute. We have y is equal to 1640 divided by 65, and it gives us about 25.2. So V is approximately 25.2 cubic feet. So it works. And we are done with section 5.2. Okay, class, so we're going to start on section 5.3, which starts on page 516 through 518. And this problem is 1 through 5 odd. So what I'm going to do, I'm going to do problems 3 and 5 from this section. So we will start with problem number 3. It says, without graphing, determine the domain of each of the following functions. Then determine the equation of the vertical asymptote for each function. Verify your answers using your graphing calculator. Okay, so we have A. We have f of x is equal to 6 over x minus 7. Okay, so first of all, we look here, we first try and find they asked us to find, well, we actually are trying to find the domain first. So the domain, remember the domain is x values. If we look here, x can be anything except for 7 because we cannot make this denominator 0. So our domain is all real numbers except x equals 7. Now our vertical asymptote is also x equals 7 because we know that graph will never hit 7. So we can go here and we can graph it. It would approach 7, but it would never hit 7. So let's go here. So we could go y is equal to 6 divided by x minus 7. Now, if you look at this graph here, let me see something here. I would want to see it a little. Okay, it will not. Okay. So if you look here, we can go all the way up this line, and I like Desmos because I can keep going, keep going. Matter of fact, let's go up here to 900. We click on here. Wait a minute. Huh. Oh, okay. I see. I took it out the picture. Let me do it like this here. We click on this line here. No matter how high we go up, it would never go past 7. It would never hit 7. So our vertical asymptote here is 7. And also our domain is 7 because it would never cross 7 on the graph as well. Okay, so now we go here to B. We have g of x is equal to 20 over 25 minus x. And then it's basically the same thing here. We're trying to find values that would not, as far as the domain, that would not make this denominator 0. So the domain is all real numbers except x equals 25. And your vertical asymptote, I'm going to abbreviate that, is x equals 25. And basically, C, D, and E basically follows the same pattern. So we have C. We have h of x is equal to 3 over 2x minus 10. Now, if we look here, of course, we could do the mathematics in our mind, but if not, let's just say you can't just look at this and tell what would make this denominator equal 0. What you could do is set this denominator equal to 0, and that will give you the restriction on your domain and also your vertical asymptote. So we could go down below here and put 2x minus 10 equals 0. We add 2x equals 10, divide each side by 2, and x is 5. So we know that x cannot equal 5. So what we would say is our domain is all real numbers except x equals 5. And our vertical asymptote is also x equals 5. Okay, now D. Now D is basically the same thing, except for we have f of x is equal to 13 over 0.5x minus 7. So we can go off to the side and take the 0.5x minus 7 equals 0. Add 7 on both sides. Divide each side by 0.5. And x is 14. So your domain is all real numbers except x equals 14. And your vertical asymptote is x equals 14. And then finally, E, we have g of x is equal to negative 4 over 2x plus 5. And we'll set the 2x plus 5 equals 0. Subtract 5 on both sides, and 2x equals negative 5. Divide each side by 2. And x is equal to a negative 5 halves is the same as saying a negative 2.5. Or you could have left it as a negative 5 halves. And so the domain is all real numbers except x equals negative 2.5. And the vertical asymptote is x equals negative 2.5. And that took care of problem number 3, A through E. So now we come here to problem number 5. It says, as the input value of a rational function gets closer to a vertical asymptote, the output becomes larger in magnitude, approaching either positive or negative infinity. Consider the functions. Now we have these functions. We have f of x is equal to 10 over x minus 5. And then we also have g of x, which is equal to 10 over 5 minus x. Now it says for 5a, it says determine the equations of the vertical asymptote for functions f and g. Now if you look here, what would make both of these denominators equal 0, which would be the restriction on the domain, would be 5. And this vertical asymptote also would be 5. So as x equals 5 would be the vertical asymptote. Now b, it says describe what happens to the output value when x is near the vertical asymptote but to the right of it. Okay, so for f of x, it gets larger and it approaches infinity. G of x gets large in magnitude in a negative direction. Approaching negative infinity. Now, what we would need to do, let's see it. Okay, so first we would have 10 divided by x minus 5. Supposed to put y equals. All right. And then we would have y is equal to 10 divided by 5 minus x. All right. So let me expand this out. All right. So let me take off the purple. So we know that this is f of x. Now it says here, describe what happened to the output value when x is near the vertical asymptote but to the right of it. Okay, this is to the right of the vertical asymptote. And as you see, f of x gets large as it goes to the right of the vertical asymptote. And it approaches infinity. G of x, on the other hand, actually gets lower as it goes down. It goes down, however, in magnitude. You know, if we're looking at magnitude, we're saying like it'll go to like negative 1 million. Now, magnitude is getting larger, but it's going to the negative infinity side. Okay, so now that's basically it. Well, hold on, that's basically it from the graph. You see here to the right, and that's basically what's happening with the outcome. Okay, now the next thing here, we go here to C. It says describe what happens to the output value when x is near the vertical asymptote but to the left of it. So we can say f of x gets large in magnitude in a negative direction. approaching negative infinity. G of x gets large, approaching infinity. Now, okay, so looking at this graph here, remember we're approaching the vertical asymptote from the left. As we go from the left, if you notice here, and this is the f of x formula, if you notice, the graph is going downward. So it is approaching negative infinity. And we know that in magnitude, we're almost talking about the absolute value of it. Okay, so now we go here to the g of x. Now remember, approaching from the left side. As we approach the vertical asymptote, if you notice here that the y values is continuing to go up, so that is the final answer here. So we see here that it's going towards infinity. Now, just to give a little bit more clear answer, when I talked about basically B, looking back here at the g of x, remember we was approaching it from the right side, going here to the vertical asymptote, and if you notice, it's going down. And then here, if we go here, again from the right side, the f of x was going up. So that's how we got the answers for B as well. So we are done with sections 5.1 through 5.3. If you have any further questions, feel free to email me. Thank you.